Today we are going to start on direct detection. So quick recap of last two lectures and quick comment on last two lectures. So I was motivating sub-GeV dark sectors where we need some kind of light mediator to set the relic abundance, and then I introduced a couple of different scenarios where we have potentially different observable handles on looking for such a sub-GeV thermal relic. So I wanted to make one quick comment on the secluded case because I sort of glossed over a possibility. So we looked at this case last time, and I was mainly focusing on what the cosmology was if there was absolutely no coupling at all of this mediator, for instance, to the standard model. But of course, I should mention that there are lots of models where this mediator does decay back to the standard model, E plus C minus, and that gets around kind of the ineffective bounds I talked about if this happens early enough. It also gets around BBN, and that's another popular class of models. And then I've been focusing on the dark photon portal, again, because it's something that appears a lot. You'll see in like dark sector reviews, but it's absolutely not the only thing that we can consider. So we have this kind of coupling through a kinetic mixing. And we're going to kind of focus, we're mostly going to focus on this kind of interaction where it could be in equilibrium or not. That was a thermal freeze out or freeze in. And this was for dark matter masses of order, say, MeV to 10 MeV, or anywhere, up or down an order of magnitude. Okay, so having motivated these kinds of light-dark matter benchmarks, I'm excited to get to the fifth lecture where I can talk about the new direct detection prospects, or new directions in direct detection, where we can get to sub-GeV dark matter. But today we have to make sure we're all kind of on the same page with respect to standard direct detection of WIMPs. Okay, so any questions on last time or where we're going?
What are the defining features of a dark photon? Like what makes it a dark photon as opposed to a dark anything else?
Just a massive vector, or it doesn't even need, yeah, massive vector, let's say, that has a kinetic mixing is what people mean. Okay. It's a dark photon, yeah. Okay. So this will be direct detection from a theory point of view, since this is a theory school. So we know that we live in some sort of dark matter halo. And our picture is, I think Dan had a good picture earlier, we have our disk. And that we imagine is rotating on average around this galactic center. And then we have this dark matter halo, it's much bigger. And all the dark matter particles are kind of, we imagine, moving randomly, sort of like the stellar orbits that Dan drew. So there's an isotropic distribution in the galactic frame. So we know it's there, and we want to see if we can detect a small scattering of a dark matter particle in our lab. And this is an important complementary approach to collider searches, because we know that the dark matter is there, so if we detect something, we can sort of relate it to something that's in our halo, something that's stable on cosmic timescales. And the fact that we're in the disk, moving along with this flow of the disk, and the dark matter is isotropic, means that we see a dark matter wind on average coming at us because we're moving in this, this bath of dark matter. So here's the sun. We're around it, and on average, there's a dark matter wind due to the motion of the sun. Of course, this is not very accurate. It's going to be like this. On the sky, it's in the direction of Cygnus. This is the WIMP wind. So this is a direction that started up 1980s or so, and has mostly focused on nuclear recoils, because if we have a WIMP in here, it can leave it can deposit energy, it can scatter off a nucleus coherently, and deposit a fair amount of energy. So as warm-up, I wanted to work through the kinematics of this nuclear recoil. And again, it'll be important when we go to sub-GeV dark matter and see why it doesn't work so well, why nuclear recoils don't work so well for sub-GeV dark matter. So define this nucleus, or this scattering event, to have a dark matter with momentum p. It goes out with momentum p prime. Let's just make these 3 vectors, since everything's non-relativistic. And I'll allow initial momentum of the target nucleus k, but in general I can just set it to, sorry, this end of chalk is it, k to be 0. The nuclei are more or less at rest. And then they go out with momentum k prime. This is my n. So we often use a quantity q, which is the momentum transfer. When the nucleus is at rest, of course, it's just given by k prime, okay, minus k, or p minus p prime. So I'll refer to this quantity a lot. Okay, so that's momentum conservation, and then I have want to conserve energy. So sorry, the initial energy is just p squared over 2mx. This is the recoil energy of the target nucleus, and then the recoil energy of the dark matter. Sorry, minus q. Okay, this piece of chalk is annoying me. Okay, so that's energy conservation, and then I can just rewrite this. Yes, so good question. Everything is, I'm using 3 momenta. Everything is a 3 vector, because I'm going to go to the non-relativistic limit. All these velocities are all 10 to the minus 3. So I'm going to work mainly with 3 momentum. If I ever use a 4 vector, I'll tell you. I don't think I will in this lecture. Okay, so if I cancel this part, so I get 0 is equal to these 3 things. And I can rewrite these 2 terms in terms of the reduced mass between the dark matter and the nucleus. And if I cancel out the q's, then I get a relation between the initial momentum and the momentum transfer of the event. And I have a cosine theta. And what I do is I look at this and I say cosine theta only ranges from minus 1 to 1. So the maximum Q where I satisfy this equation, the maximum momentum transfer, is when cosine theta is 1. So I just set cosine theta equals 1, and this is the maximum momentum transfer. And I want that because I want to see how much energy can I deposit in this nucleus. What is the maximum energy I can deposit? And that corresponds also to the maximum momentum transfer. So combining the energy and momentum conservation, I'm getting that the maximum momentum transfer, I can also rewrite this initial momentum is just mv. And so the maximum momentum transfer is given in terms of the reduced mass times the dark matter velocity. Okay, and if we look in the limit where the dark matter mass is much less than the nucleus mass, then the reduced mass, sorry, this is a bit low. So there's the reduced mass. And in the limit where the dark matter mass is much lighter, this reduced mass looks like just the dark matter mass itself. And our momentum transfer is just 2mv. So that's what we expect if we have a very heavy target and the dark matter just hits it and bounces right back. And then we use this result for the maximum momentum transfer to get a maximum recoil energy. Sorry. Okay, so let's plug in some typical numbers for both of these cases. If my dark matter mass and my target mass are both around 10 GeV, then my reduced mass, let's just pick an arbitrary number, around 10 GeV, let's say. And the dark matter velocity is about 10 to the minus 3. This is going to be on the order of, let's say, 10 or whatever, 10, 20 keV. No, sorry, MeV. And if I plug in 10 MeV squared over 2 times the target mass, that will be closer to 10 keV. So these are the kind of typical numbers that you'd see for most nuclear recoil experiments. We can also turn this around and say something about what the velocity of the dark matter has to be in order to give us a certain amount of recoil energy. So I just rewrite this equation. To write this. Okay. So as expected, to get more recoil energy, we have to start increasing the dark matter velocity, and that will matter because we will have a cutoff in the dark matter velocity of order the escape velocity locally. Okay, let's see what else these estimates have told us. We look at this maximum momentum transfer, about 10 MeV. We can compare that with the size of a typical nucleus. So there's a big scaling with the atomic number, but let's just write it this way for something in the A of order few tens. So that will be the radius of the nucleus. And if I turn that into 1 over Rn, it'll be about 10 MeV also. Okay, so what that means is for this kind of momentum transfer, it is possible to scatter off the entire nucleus, because we can compare the size of the nucleus is sufficiently small compared to the, or at least on the order of the momentum transfer, so coherent scattering is possible. Meaning we can take advantage of the fact that there's lots of nucleons. We get cross sections that are proportional to a squared times sigma n, but there will be some sort of form factor we have to take into account because these are not extremely separated, they're still comparable. We can also compare the recoil energy with typical splittings in a nucleus. So that will be on the order of MeV. So we know we don't really have enough energy to excite one of the states of this nucleus. We're probably just going to recoil off the nucleus. If we look at the atomic states, here it's a little bit more tricky. These will be on the order of these can be of order keV, so similar to the recoil energy, and this is a very tricky part, modeling exactly what happens when you hit the nucleus or hit the atom, what happens to all the electrons. That's a complicated question which I will not attempt to address. Okay, so that gives us an idea of the relevant ingredients that have to go into thinking about nuclear recoils. For today, I want to go over the kind of steps to calculate direct detection cross sections, but mainly focusing again on just how to estimate things quickly, like the spin dependent, and getting intuition for how the dark matter velocity distribution impacts the expected signals. Okay. So these are the steps to calculate the dark matter direct detection rate. So first, if you have a very heavy dark matter candidate, you might need to do some running of your operators from your heavy scale down to the QCD scale. So that's covered in your EFT lectures. So I will say no more. At this point, I might have operators that look like this, still in terms of QQ bar. And I need to match these on to nucleon level operators. So nucleon, single nucleon operators. These nucleons inside the nucleus are non-relativistic. So here I'm going to take a non-relativistic limit. And at this point, then I can match onto the nucleus level. So I need to go to the... and there are different ways to do it. There's, for instance, a big set of papers recently that, given your non-relativistic limit for the nucleon operators, they tell you what the appropriate form factor for scattering is to go to match onto the nucleus. So this is the EFT of direct detection set of papers. I'll just write the main one. And then kind of do all this for fixed dark matter velocity, and now we need to account for the dark matter velocity distribution. Okay, so as I said, I'm skipping step 1 and I'm just going to talk about step 2 and identifying things like spin independent and spin dependent and matching onto this non-relativistic EFT. Okay, so as my examples, I'm going to just consider WIMPs scattering through, for instance, a Z or a Higgs, and consider a couple of different operators. So this is just some vector coupling, and I'll normalize it, the Z mass. And then I'll also do Higgs mediated. And here, since I want to write down something that, well, if I'm scattering through Higgs, I'm going to go through the Yukawas, so I just normalized it with the quark masses over V, or the Yukawas.
I'm sorry, the superscripts on the C's, tell me.
Oh, I just labeled this for scalar, axial, or vector for the type of, yeah, just some arbitrary order 1 coefficient.
Sorry, these are higher dimensional operators?
Yeah, so I assume that step 1 has already been done. You say I have some dark matter candidate scattering through these, and I've just already integrated out the Z and gone down to the QC scale.
So you know how to scale?
These are all fermionic dark matter. Yeah. Is there a question? Oh, yes.
Yeah, but then you have to reflect, or if you have to
Right, so if the question is if the mediator is light, yes, I have to just include the mediator in the theory, and then the procedure I'm showing you will kind of more or less be the same, but then I'll get a dark matter form factor, and I can change the momentum, the recoil spectrum, and so on. So, yeah, that was actually an important point I wanted to bring up at the end, that everything I'm doing is, and everything most of the things that are being done for nuclear recoils assume these higher dimension operators and don't allow for light mediator. Oh, I'll write it as Higgs Vev. It's Higgs Vev. Yeah, it's not too important because I won't really deal with the specific coefficients, but yeah, I meant Higgs Vev. So let's just look at the vector operator for now. And I want to match this onto a nucleon level operator. So I need to calculate basically this quantity. So there are lots of these kinds of matrix elements within direct detection of various quark operators within the nucleon. For the vector, at least, we can write down the general behavior of whatever this matrix element is. We know it should map onto something that looks like this. Did I get my... So I'm going to use little n for the nucleon and big N for the nucleus. At least that's what I will try to do throughout.
N bar is an antinucleon?
Oh yeah, my notation's a little weird. Yeah, let's just write it, or sorry, I meant to, let's make this uniform, yeah. So the matching will be from this Q bar gamma mu Q onto an operator with nucleon spinor states with this structure.
So wait, is N bar an
Yeah, it's like I'm changing the Q bar Q into an M bar N, yeah,
Okay.
basically, yeah. I'm kind of glossing over the fact that I have multiple quarks in the nucleon. Let's neglect that for the moment. I should sum over all the quarks in the nucleon, but in any case, this kind of matching will result in, well, first I can just write down the most general thing that is possible with these form factors. In the Q going to 0 limit, this approaches 1. And again, I have to be careful here because if it's an up versus down and so on, but let's just take the limit, where I can take this to be 1. So effective charge of the nucleon is the same as the effective charge of the quark. That's just by charge conservation. I know the behavior of this first form factor. To get the form factor away from Q going to 0 requires, as far as I know, requires lattice calculations. There are people working on this. But for most purposes, typically it's a good approximation to take Q going to 0. So again, that's because everything we're looking at is pretty non-relativistic. So that also means whatever the second piece is, it's going to be suppressed by at least 10 to the minus 2, 10 to the minus 3 because of this momentum over Mn.
And that Q has become a full momentum now? Because you've got Q new.
Yeah, if I put in this case I put a for momentum label, so it's the for momentum. Yeah, so this piece will get suppressed generally.
So you said there's a sum over the quarks on the left side. Have you not there?
Yeah, I was being shady here. Okay, so if I take like the U quark, then I need to just count the number of U quarks. So this becomes 2. If it's, well, it depends which nucleon. If it's a proton and I have U quarks here, then this form factor is actually 2. So I have 2 U quarks. So I just need to do that. I just don't want to go into if neutron versus proton. Yeah.
So you can say that those Q's is a weighted sum.
Yeah. In this case, I'll just make a weighted sum.
This might be a really dumb question, but what does that Q operator indicate happening physically?
Sorry, this operator?
What does the operator represent physically? What actually is that?
So in this case is a little simpler because I know this is a conserved current or conserved current, so charge. So I can also say that in the Q going to 0 limit, if I have a conserved charge, it should be the same charge as the nucleon.
Okay.
Yeah. The other cases are a little harder to interpret sometimes. Okay, so this is to argue that we can drop a lot of things, and the approximation made is that this just becomes n bar gamma mu n, again up to the fact that I should sum over the appropriate quarks. So this is still the Lorentz, well, we're still using 4 vectors, and the next step is to take the non-relativistic limit. And the way that the operators are classified in the non-relativistic limit, at leading order, is instead of using Lorentz invariance, they use Galilean boost invariance. Meaning if I boost my 3 vectors, my 3 velocities, then the result should stay the same. So all of the physics should depend on relative velocities or relative momenta. So the possible non-relativistic, the operators I can write in the non-relativistic limit, 1 is always an operator. Q is a good operator because it's a difference of, it's a momentum transfer.
I feel like you have 2 Q's on the board right now. One of them is a quark thing, and one of them is the momentum transfer. Can you just make...
Yeah, yeah. I don't know how to make these Qs. If it's a Q bar Q, it's always going to be a quark.
If it's not,
Yeah.
if it's not, then you have to.
I will, yeah, I'll put a little hat over my vectors.
Thank you.
Yeah. The relative velocity, so this is V, well, let me write, sorry. The relative velocity of the dark matter and the nucleon is another operator. So here I'm working at the nucleon level, so this is the nucleon mass here. And technically what this direct detection of EFD paper does is it makes these two orthogonal, but for us, let's just keep it as the relative velocity. We have the spin of the dark matter and the spin of the nucleon, where I'm just going to use this vector to denote, well, yeah, you know what it denotes. It's a vector. But these are, can think of these as operators. Yes?
So it seems to me that you're trying to see what happens when the first operator interacts with the nucleon.
Mm-hmm. Mm-hmm.
Then why don't you have the chi bar gamma mu chi inside that?
Yes, good. So why have I'm ignoring the chi bar gamma mu chi for now, just because I don't need to worry about matching onto the nucleon, and I'll reintroduce it in just a second. Yeah, for this part it was just for matching onto the nucleons. So these are scalars, these are vectors, and these are parity odd vectors. So if I look at this n bar gamma mu n, just kind of decompose it into the scalar part and the vector part, 3-vector part. And I can use the fact that my operators have to be written in terms of one of these above non-relativistic operators to simplify this, or to figure out what the behavior is. So this is a scalar, right? So that's fine. Scalars are good. And you can look at the dimensions of the spinners in, well, so if we look at the dimensions of the spinner states, then we'll get something like 2, maybe there's a 2 mn. And then I'll use these squiggles for the dimensionless spinner states. Okay, so because this is a scalar, I just put in the mass of the spinner, because that's the only thing I can do in this situation. This part is a vector, and it depends only on the momenta of the nucleon. So I'm going to say it can't depend on V, it has to depend on Q. So this will look something like the same spinner stuff, but with a Q. So this part will, again, because the momentum transfer is always going to be less than the mass, this will be suppressed, and we can more or less ignore this. And we're just left with the first part, and it's just a contraction of the spin states. And so this is what's known as spin independent. Because it doesn't depend on the spin of our nucleon states. Oh, yeah, it's like a contraction of these spinners, yeah.
So it's a contraction of two objects but independent of them?
So yeah, it's independent of the particular, yeah, like this will just, when I trace over things, this will just give me like 1 instead of being proportional to the spin. So I'll show you in a second the spin dependent case. Yeah, spin independent meaning for each nucleon I kind of have the same thing and I can sum over all of them coherently. And so if I take the full operator now, I can do the same thing. I can do the same thing for the dark matter part. I know it has to decompose in this way in the non-relativistic limit, and it's going to look something like a bunch of spinner stuff again. And chi is just the one for the dark matter. So the second example is one where I have a spin-dependent interaction. So I'm again going to argue that up to some factors, which these are not easy to determine, but I'm going to skip over what exactly the factors are, the quark level operator will be matched at leading order with something like this. The same thing, but with nucleons. And now the non-relativistic limit consists of a scalar, but it has this parity odd part, and a parity odd vector. And again, using the possible operators we have, the parity odd vector has to go into the spin now of the nucleus. So this looks something like and we don't have something that immediately pops out for either of these. So for this one, we'd have to take a dot product of two of these things. And that will lead to this part, again, being suppressed by the typical momentum over the mass. Yes?
In this first case, why don't we have the Q-dependent part?
In this first case.
The chi bar gamma mu chi, n bar gamma mu n. Why do we have just the gamma 0 part and not the gamma I?
In this one, you mean why did I drop this? I dropped it because this momentum transfer over the mass is typically very small. Or typically quite small. So at leading order, this is what you get. You get correction. These are like 10 to the minus 2 corrections or 10 to the minus 3 corrections. Okay, so this is spin dependent because I explicitly get the spin operator appearing. And then if you want to do spin dependent scattering over the entire nucleus, then with the spin operator, it doesn't add coherently over the entire nucleus. And you rely on the fact that many nuclei have like a few unpaired nucleons, and that's where the spin is coming from.
What is the ideal type of nucleus to do this with?
I believe fluorine and iodine are good for spin dependent, and xenon's also not bad, pretty good.
I would have guessed the smaller nucleus was easier to see the momentum transfer on, like it's lighter, more obviously moving when it gets thick.
Yeah, I think maybe it was Pico that uses fluorine that targets lighter dark matter. I don't remember the mass though. Okay, so this kind of classification into the non-relativistic operators is, I find very useful because it helps you whenever you have an operator to quickly see if it's spin dependent, or in other cases you can have a suppression by velocity and just see what you expect. And lastly, if we look at the scalar one, that one also is spin dependent. Because, well, it's a scalar, so we can expect it to kind of behave the same way as this first part.
It's spin dependent because it can behave the same way as the first part with the spin independent.
I meant spin independent. Sorry if I said spin dependent. Yeah, spin independent. Go back here. Okay, so having now the non-relativistic nucleon level operators, you can use kind of the results here to get what the total nuclear response is for your particular nucleus. I don't want to go into too much detail, but let's just look at the scalar operator as a quick example. Again, I want something like this in the nucleus. It's my big N's. And it's going to give me some sort of form factor. Remember, because the size of the nucleus is comparable to my momentum transfer. So this is a different one. I'll put N. And it's helpful to remember that the n bar n operator in the the n bar n operator corresponds to the nucleon density. So this, a common approximation for this form factor is to just take essentially the Fourier transform of the density inside your nucleon state with whatever model you have. Something like this. So in the zero momentum limit, we're just summing up all the nucleons inside the nucleus, and we get A. And so that's where our coherence will come from, because we'll square this matrix element and get A squared. You can sketch what it looks like, and if this is A, and it'll kind of drop off pretty rapidly and do some stuff like this. This is a log scale. Xenon, if you're looking at scattering in xenon, it is kind of probing the drop off in the form factor. So getting these form factors right does matter, but we're not quite all the way in this part where it's oscillating.
Is Q here the momentum of the
Here.
transfer?
Yeah, momentum transfer, yeah.
Okay.
These are all, if it's in a form factor, it'll be like a magnitude of the momentum transfer, yeah. Okay, so now we can put this all together for our total rate. So it's usually expressed in terms of the one single nucleon scattering cross-section. Again, I'm assuming that the scattering off of neutrons and protons is the same, just to simplify things. And in terms of the operators I wrote above, if M1 is the amplitude of the operator, then the single nucleon cross-section can be written as the reduced mass of the dark matter in the nucleon times that over pi. M1 is this thing. Yeah. And then the one for the nucleus is, better look at the formula to make sure I write it right. So I have a recoil spectrum. It's proportional to the number of targets I have, the dark matter number density, this one nucleon scattering cross-section, the target mass of the nucleus. This reduced mass appears back in here because just of the way this product is, just because of the way the single nucleon cross-section looks. If my nucleus form factor, and I want to integrate over my dark matter velocity distribution. So this part already counts for the scattering or the cross-section, but then I want to integrate over the initial distribution. So that initial distribution I'm going to write as f of v and there's a 1 over v, which I'll explain in a second. So this is the full scattering rate, and this part, this 1 over v comes from the fact that if I go through and calculate this cross-section off the nucleus, there's a 1 over v squared, and then I want sigma v for a rate, so it cancels to 1 over v. I have a function here that restricts the integral over my velocity distribution to be greater than this v min, which I introduced earlier as the minimum velocity you need for a given recoil energy. What is m?
NT.
NT? It's a conversion because these things are usually expressed in terms of rate counts per kilogram per day. So it's a conversion of the number of targets per kilogram. Just a conversion factor. Or the number of nuclei per kilogram. Okay, so we've addressed most of this first part. I want to spend a little bit of time on the dark matter velocity distribution. Yes? Why does it have this form? Because I can't, once the momentum transfer is kind of order the size of the nucleus, I'm not going to sum over all of the nucleons inside anymore. So it'll be much smaller than A. It'll drop off pretty fast. Yeah, it does reach 0 for a certain momentum. It's like an interference effect. Yeah. Yeah, and actually the location of the zeros is, it's important and it changes in different models. So, yeah.
Inside the nucleus is basically constant until the edge of the nucleus. So you're calculating the form factor of a uniform sphere. Okay, and right, chapter 9. So you've got several functions that bounces square to bare, plotted on a log scale.
Yeah, it's a log
What's
scale.
happening physically is that you're getting destructive interference between the different parts of the matter and nucleus. Actually calculating these things is really, really, really hard. It's a 50s problem, but it was really hard then, and it's still really hard now.
Yeah. So, in the next lecture, I'm going to be talking about other atomic / condensed matter physics. And before you think that regular dark matter direct detection doesn't involve really hard many-body physics, I should just underline this again. Yeah.
I think that was what capital A was, though.
It's the atomic number of the, yeah. So let's do a little bit of astrophysics. I'm going to write down what the standard halo model is for this velocity distribution is. First, in the galaxy frame. Oops. So in the galaxy frame, it's isotropic, it's the same in all directions. V0 is usually assumed to be about 220 kilometers per second. Again, that's something we assume based on the motions of the stars. This is just some normalization factor to make this integrate to 1, so don't worry about it. And I cut this off very unphysically at the escape velocity, which I mentioned was around 500 or 600 kilometers per second. This is definitely not a realistic velocity distribution in that we expect for the actual, you can look at simulations, maybe Mark will talk about that, and it's It does not have this behavior. It definitely does not have this behavior near the tail, but we use it just as a approximation in order to do these calculations because we don't know exactly what this velocity distribution is. Okay, so it has kind of this, it's called the isothermal model. It's related to the isothermal model. And in the Earth's frame, I have to boost this thing and I'm going to boost it by the Earth's velocity, which I decompose into the sun's motion around the galactic center, plus the orbital motion of the Earth around the sun, and the theta function is the same. I just have to include this boosted stuff inside, which I won't write out. Okay, so this accounts for this boosting is what gives us the WIMP wind along mostly the sun's velocity. So the sun's velocity, let me just write it down, is about, varies, but similar to the velocity dispersion. So that's why it's not a very directional wind. And the Earth's velocity, hope I got it right. I think it's around 30 kilometers per second.
Is the Earth velocity being measured with respect to the sun? Or the
Yeah, this is orbital.
Okay.
Yeah. So this time dependence means, well, we get so there's a time dependence here. The direction varies. So that's where we can see things like annual modulation, directional detection, all that. That's all in here. And I can just sketch this out in the lab frame. So this is f of v, and it'll just behave like you expect. It'll peak somewhere around 200 kilometers per second. Yes? Mm-hmm. Yeah, so the question is how much the rates change if I allow deviations. They can change by a factor of a few, depending on the mass of the dark matter. Usually, from what I've seen, if the dark matter is pretty heavy, the change isn't huge, but if the dark matter is light, the change is pretty big. And let me actually, I was about to explain something related to that. Here, I have a little bit of, sorry. So, I'm going to sketch this again. And we have an integral where we have to put a lower boundary where the minimum velocity is, which is set by the recoil energy. So it could be something like this. Whoops. And if I have, okay, so it'll be something like this, and I want to integrate everything above here. If I have very heavy dark matter, I'm going to just keep increasing this reduced mass, and that pushes my minimum velocity down, and I integrate over more and more of this. And if I have lighter dark matter, it pushes this up, and I integrate over less of this. So typically, I've seen that if we see that for pretty heavy dark matter, you're integrating over a lot of this velocity distribution. Then even if there are changes in the particular shape, the limits don't change a ton because you're already integrating over, you're kind of averaging over everything anyway. Whereas if you have very light dark matter and there are, streams or some other change in the behavior in the tail, then you can get a pretty big effect in what the limits look like, because you're only integrating over this tail.
Since the galaxy as a whole rotates together, in the same direction, so we have an indication that the halo itself does something similar. So, would we see that the velocity of dark matter relative to us would be noticeably decreased by being in the same direction?
I think the evidence is that there's no evidence for a part of the halo that's rotating. You can look for things like a dark disk that's rotating. There could be, however, maybe streams, so that's that would also change your distribution. But so far, there's no evidence of a part of the halo that's rotating with us. Okay, and this minimum velocity explains a lot of the behavior of the recoil spectrum that you would see when you compare with these experiments. And so that comes from just integrating this f of v, and I'm going to just drop the part. So I'm going to go to the very tail of this distribution and just ignore this, this part due to the Earth's velocity. So then I can just take the isotropic limit and replace this integral with v squared f of v. Just, yeah, something like v escape. No, I'll write this. So the behavior on the tails will be something like this. This is an integral we can do on the board. It just becomes an exponential. So it's an exponential in V min, and if I plug in now V min, which is the square root of the recoil energy, I get an exponentially falling distribution in the nuclear recoil energy. Okay, so it's exponentially falling over this combination of things, and this combination of things is kind of the typical scale you expect for the nuclear recoils. So remember, we derived that on the very first board that the momentum transfer is going to be of order 2 times the reduced mass times velocity. And so if I replace that with the initial velocity dispersion, this sets the scale for that exponential fall off. These are all nucleus, yeah. Okay, so if I look at what this recoil spectrum, if I look at the recoil spectrum as a function of E of r, I can just sketch this exponential fall off for different dark matter masses, something like this. One more color. So this would be like mx of 100 GeV on xenon, and then as I reduce the dark matter mass, this fall off will become steeper due to this reduced mass dependence. So let's say this is about 10 GeV. Potentially below whatever the threshold is of the experiment. Yes.
So, the slope of these plots, they should also depend on the mass of the nucleus.
Yes, here I took a fixed xenon target just as a sketch. Yes, you're right. They depend on the nucleus. Okay, so in the last couple of minutes, let's just look at, or I'll sketch what the xenon 1 ton results look like, and we'll discuss a little bit of the model implications and the behavior of their limits. So you might have seen recently, in the past few weeks, we had new results from the xenon 1 ton year. They set limits on this spin independent, 1 nucleon cross-section versus dark matter mass. It's an incredible cross-section. It's about a few times 10 to the minus 47 centimeters squared. And the max was around 20 or 30 GeV. Okay, so these big ton scale experiments they're using xenon, where A is about 130, so they get a big coherent enhancement. They have a huge target mass, and they suppress backgrounds as much as possible. In the next, hopefully I'll have time in the next lecture to talk a little bit about the approach they take for nuclear recoils, and why that can also be extended to look for electron recoils for light dark matter. But okay, so here's xenon 1 ton. We have that the behavior of their limit in the very high mass part goes as 1 over mx. That's because everything in these integrals, everything out here, the dependence on the dark matter mass kind of drops out. All the reduced mass, all the factors of reduced mass just turn into either the nucleon or nucleus mass, and we just get the 1 over mx, where this is, again, fixed to be, the energy density is the fixed value. So they drop off in the high mass regime as 1 over mx. And we've seen why they also drop off in the low mass regime. It's due to this fact that we get an exponential suppression, where the scale decreases as we decrease the dark matter mass. And then it drops below the threshold. So again, these are targeting weak scale dark matter, or WIMP dark matter. So let's just want to comment on a couple of benchmarks in this parameter space that people have discussed. One is Z-mediated vector, obviously, because it's spin independent. And that's just the first operator above. And if I just set C, V up there to be order 1, or at least put in some gauge couplings, this is going to be around 10 to the minus 37 centimeters squared. So already 10 orders of magnitude above the current limit, or the best current limit.
Does above mean should have seen or can't be seen?
Ruled out. Yeah, and I guess I should comment that these limits do drop off somewhere up there where the dark matter doesn't reach the lab anymore because it scatters through the Earth. But most of those gaps, even if the direct detection stops, they're closed by other constraints. Higgs mediated was the second one. It's also the third scalar operator, and it's also spin independent, and I get a suppression due to these Yukawas and so on. And just setting, again, an order 1 coupling, this is about 10 to the minus 43 centimeters squared for order 1 coupling assumed up there. And these were kind of generic, but I can look at specific things like a doublet or pure triplet, pure electroweak doublet or triplet, or AKA Wino or Higgsino. These are similar to the Higgs mediated, so you really have to go through all the steps I mentioned before, and for that you can see a series of papers by Hill and Salon. And so by doing the running from the heavy scale down to the weak scale, they find a number of different operators contributing to the spin-independent cross-section. And so even though there is this Higgs-mediated component, they kind of get suppressed, and they find, due to the cancellation, and they find that the cross-section is around 10 to the minus 47 for, which one? For pure triplet, and then it's even lower for pure doublet. So these are simple extensions to the standard model. They're just electroweak multiplets. In principle, you could get a thermal relic up at a few TeV, and it's below the current direct detection constraints. But there are some pretty strong indirect detection constraints on the pure Wino case, which Tracy has a paper on this. Maybe Dan will talk about it. We'll see. Yeah. Yeah, from Hess. Yeah. Okay, so that's sort of the landscape. This fact that the generic Z-mediated and Higgs-mediated scattering cross-sections are larger than the cross-sections makes model building pretty difficult, though there may be some room for these like electroweak multiplets, which have pretty low cross-sections. They're going to take a while to get to. Okay. So I've presented the nuclear recoil, and we've seen that it's not ideal for low mass dark matter because of this drop-off. Particularly the maximum, let's see if I still have it. No, I erased it. The maximum nuclear recoil energy drops very fast when I have a light dark matter candidate. It drops as the dark matter mass squared. So this was the maximum recoil energy for a given velocity. And it drops as the dark matter mass squared. So it's not going to work for the sub-GeV dark matter I talked about. It also doesn't capture the fact that when I have a light mediator, I want to include I need to include that fact if I have a light mediator, and none of these include any momentum dependence. Whereas if I have a light mediator, I'm going to want to have something like this. And it could be that the mediator is sufficiently light that I get just 1 over q squared. 1 over q squared, remember, is basically like 1 over the recoil energy. And so I get a big difference in the recoil spectrum where a lot of it has shifted to lower energies. Okay, so we need some sort of way to get to much lower thresholds in our detector if we want to get to low mass dark matter, both for the kinematics of light dark matter scattering and if we have light mediators, because the recoil spectrum gets enhanced even more at low energies due to the 1 over q squared dark matter form factor.
How do you control for anything else that it is? So like, presumably at some point you have to, like neutrinos can bounce off of things. It doesn't happen often, but
Yeah.
if we're talking about something as weakly interacting as dark matter, then it's probably the same order of likelihood. How do you tell what bounced off your nuclei?
Right, so question of backgrounds. Right now we don't have many, we're not at the neutrino floor, or we're not at the point where there's many neutrino events. There is, we're close in the xenon detectors. They're trying to detect solar neutrinos. So most of the backgrounds are things like radioactive decays.
Random motion of between nuclei? Like,
Yeah, there's just lots of alphas, and there's electron scattering, which isn't a nuclear recoil, but then some of the energy is lost, and it looks like a nuclear recoil. So yeah, there's definitely lots of backgrounds which are very hard to control. So I apologize as a theorist, I'm skipping all of that. What's that?
I was thinking, especially when you get to a really low recoil energy, there's a lot of things that would look like a small recoil.
Yes, yes. Actually, the radioactive decays I'm talking about, they deposit a lot of energy, so they actually don't look too much like a low energy dark matter recoil. But there are lots of other things you have to worry about. Okay, so that's it. In the next one, the next final class, come to the last one, because that's all new stuff. It's all going to be electron scattering, phonon scattering, and light dark matter, and a summary of some of the experimental directions. That's it for today. Thank you. Yes?